When you first start your NDT journey, most of your theory training happens up front. But by the time you log all your on-the-job training hours and you're finally eligible to take the exam, that classroom knowledge isn't always fresh anymore. That's where the Liquid Penetrant Test Prep app comes in. With this app, you can keep your theory sharp while you build hands-on experience. It features 2 learning modes. Study mode gives you instant feedback and clear explanations for every question, helping you understand why each answer is correct. Test mode recreates the pressure of the real exam so you can strengthen your focus, speed, and confidence. Study anywhere, on breaks, in the field, or at home. The app tracks your performance automatically, showing you exactly where to focus next, so every minute of study moves you forward. Download the Liquid Penetrant Test Prep app today on the Apple App Store and take the next step toward a safer, stronger career in non-destructive testing.
Welcome back to the Deep Dive. Today, we're taking you on a bit of a tour through the world of flaw detection.
Specifically looking at liquid penetrant testing equipment.
Exactly. We're digging into the source material titled Liquid Penetrant Testing Equipment to understand, the whole spectrum.
From the real basic kits you might see for maintenance.
All the way up to these, huge automated systems for critical parts, jet engines and things like that.
Yeah, it's quite a range. And the goal, as always in NDT, is finding those discontinuities without damaging the component itself.
Right, and the equipment you choose, well, it dictates a lot. The cost, how fast you can work.
And the reliability, too. Big factors.
Definitely. But before we get into classifying all this gear, we've got a quick message from our sponsor. Today's episode is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. You can learn more about their services at the link in the video description. Okay, thanks. So let's try and map out this landscape. The sources point to, 3 main categories of equipment.
That's right. They really help frame how you choose based on need. First up, you've got the really simple stuff. Portable, hand-operated equipment.
Easy to move around, yeah, for spot checks.
Exactly. Think field repairs, maintenance checks, occasional use, lightweight, basic.
Okay, then what's the next step up? When you need something more permanent?
Well, that's when you move to the larger, more complete stationary equipment. These are kind of the workhorses,
General purpose, they call it.
Yeah, general purpose. Designed to handle a pretty wide variety of parts, different shapes, different sizes, as long as they physically fit in the tanks, of course.
Makes sense. And the third type?
That's the top tier. Specialized units. These are custom built, often for really high volume production lines.
Like conveyor belts moving parts through.
Precisely. Often designed for just one specific type of part, aiming for maximum efficiency and super consistent results.
All right, let's start in the beginning then. The portable kits. If I'm just doing a quick checkout in the field, what's the absolute minimum I need?
For visible dye testing, it's surprisingly simple. Just 3 spray cans, really.
Okay.
You need the liquid penetrant itself, the cleaner or remover, and then the developer.
And lighting. What about that?
That's the beauty of visible dye. Just good shop light works fine. Or even a decent flashlight if you're, in a darker spot. You see the red indications against the white developer.
So, super simple, no special lights needed. But fluorescent penetrants are more sensitive, right? What changes then?
Yeah, that definitely changes the gear. You swap out the visible materials for fluorescent ones, obviously.
And that means?
You absolutely need a portable ultraviolet lamp, a UV light, and you also need some way to darken the area.
Like a little shield or a hood?
Exactly. Something to block out the ambient white light. The kits themselves are usually low cost. They come with everything you need in a case.
But there's a catch.
Well, the sources are pretty clear on this. For reliable results, especially finding faint flaws, you really need proper dirt conditions. Minimal ambient light is key. It's not always easy to achieve perfectly in the field.
Okay, so portable kits are great for occasional stuff, but if you're doing, say, dozens of parts every shift.
Yeah, you can't really rely on just spray cans and trying to rig up a dark space. You need consistency.
Which brings us to that second category, general purpose stationary equipment.
Exactly. These stationary systems give you the structure, the control you need. They range quite a bit, from smaller units doing just a few parts an hour
to bigger ones for moderate production.
Right. The key thing is they provide all the necessary steps in one place: application, washing, developing, inspection. And the part handling is usually pretty straightforward, maybe manual or using simple roller conveyors or hoists.
Let's zoom in on the smaller end. The sources mention these self-contained units, maybe taking up about 3 square meters. designed for water-washable penetrants.
Yeah, those are pretty common for smaller operations. They pack the whole process into a compact footprint.
Walk us through the steps. What happens first?
Okay, so first is the liquid penetrant dip and drain station. Parts get dipped in the tank, or sometimes you might brush the penetrant on.
And the draining part is important.
Very. You need to let the excess drain back into the tank. Saves material, saves money. Plus, critically, the part has to sit there long enough for the penetrant to seep into any flaws. That's the dwell time.
Right. Can't rush the dwell time. Okay.
Yep.
After it dwells.
Then it moves to the wash station. Since we're talking water washable here, this is where the operator rinses off the excess penetrant from the surface, usually with a water hose or a spray nozzle.
And there's a special light here.
Yes, very important, especially if you're using fluorescent penetrant. There's a UV light overhead.
Like a first quality check.
Exactly. The operator uses that UV light to make sure all the extra surface penetrant is gone before the part moves on. If they don't wash it off completely, you'll get false indications later. Big problem.
Gotcha. So wash is done properly. Next.
Into the parts drying station, usually a recirculating warm air dryer.
Needs to be temperature controlled, right?
Absolutely. Thermostatically controlled. Too hot, and you could mess with the indications, maybe even bake the penetrant on, making it hard to see flaws once it's properly dry.
Time for the developer.
Yep, the developer application station. How you apply it depends on the type.
Like dry powder versus wet.
Precisely. Dry powder developer. Part has to be totally dry. Aqueous or water-based developers, those can sometimes go on while the part is still a little damp from the wash.
And the developer also needs time to work.
It does, another dwell time. This lets the developer act like a blotter, drawing the trapped penetrant back out of any tiny cracks or pores to form that visible indication.
Okay, and then the final step.
Yeah.
Inspection.
The inspection station always needs to be a controlled space, usually an enclosed booth, maybe dark curtains.
Light proof?
Ideally, yes, especially for fluorescent. It needs the right lighting inside adjustable UV sources and also white light sources so the inspector can really examine the part surface properly.
That sequence makes sense for a compact unit.
Yeah.
But you mentioned earlier they have size limits. What if the part's just too big for the dip tank?
Yeah, good point. That's when you move beyond the self-contained unit into what they call multiple component stationary systems.
Modular, you mean? Like building blocks?
Kinda, yeah. Instead of one box, you have separate stations. Dip tank, wash station, dryer, developer, inspection booth, arranged how you need them. Straight line, L-shape, U-shape.
More flexible.
Much more flexible. Handles higher production rates and, crucially, much larger parts. The sources mention dip tanks for these systems getting huge, like over 60 cubic meters. Definitely not fitting that in a small footprint.
Wow. Okay. So that bridges the gap. Now let's push into maximizing output, getting really consistent results. That's the high-volume, custom, automated stuff, right?
That's the top end. These specialized production units, often with conveyors moving parts automatically, they give the most uniform, most repeatable liquid penetrant testing.
Total control over the process.
Positive control, yeah. Fixtures hold the parts just right, material application is consistent, timing is precise, every step is managed.
And the driver here isn't just consistency, it's speed, right? Keeping up with production.
Oh, absolutely. Think about something like aircraft turbine blades. You might need to inspect thousands of those an hour.
Wow.
Manual lines just can't possibly keep up with that kind of demand. Automation is the only way, and it minimizes the risk of processing errors, washing too much or not enough, dwelling too long or too short.
Right. It eliminates some of that human variability.
Yeah.
And we see this customization in aerospace a lot. Big tanks for big parts.
Definitely. The sources talk about custom dip tanks, maybe 30 meters long, just for large airframe sections, using complex overhead hoists to dunk these massive structures.
And they change how they apply the penetrant too, not always dipping.
Right. Dipping is simple, but for high volume, spraying is often more economical. Conventional air spray or even better, electrostatic spray.
Why is spraying more economical?
Mainly because it cuts down massively on dragout. That's the penetrant that clings to the part when you pull it out of a dip tank and gets wasted. Spraying uses much less material overall.
And electrostatic spray is even better. How does that work?
Yeah, electrostatic is really efficient. You give the tiny droplets of penetrant an electrical charge,
Okay.
and the part you're testing is grounded. So the charged droplets are strongly attracted to the part surface, like little magnets.
So it wraps around complex shapes.
Exactly. It wraps around, covers thoroughly, but uses way less material. Some sources say electrostatic systems might use only 10% of the penetrant compared to a dip tank.
10%. That's huge savings.
Huge savings, Less material cost, less waste to deal with, less pollution. It's a big win-win.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's podcast. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com. That efficiency is incredible. Okay, so let's picture a typical conveyor system. The source mentions tractor castings as an example. How does that flow work?
It's usually a continuous movement. Parts get loaded onto the conveyor, move through a spray booth for penetrant application.
Then a drain area.
Yep, drain and dwell time as it moves along.
Yeah.
Then into a water wash cabinet, then maybe an air blow-off to remove excess water, through a drying oven.
Then cooling.
Sometimes a cooling station, yeah, before it reaches the inspection booth at the end. It's all automated, moving at a set pace.
And that fixed speed. That's a drawback, isn't it?
It can be, yeah. The conveyor speed controls everything: penetrant dwell, wash time, developer dwell. There's not much flexibility. If one part needs a longer dwell, you have to slow the whole line down.
Right. Not ideal for mixed batches, but the newer automated lines, like for aerospace, are probably smarter.
Oh, much more sophisticated. Parts are often loaded onto racks on an overhead conveyor. They go through rigorous pre-cleaning first, maybe alkaline cleaning, rinses, even acid pickling sometimes.
That'd be perfectly clean.
Absolutely critical. Then automated penetrant spray, often electrostatic like we discussed. Then a really controlled water wash, maybe with adjustable nozzles, hot air drying, developer application if needed. Then finally, inspection, highly controlled.
Okay, all this complex machinery. But it still comes down to someone looking at the part, right? The inspector's eye.
Ultimately, yes.
Yeah.
Which brings us to the lighting and vision requirements. Getting that inspection environment right is absolutely critical.
Couldn't be more important.
Yeah.
Let's talk about that. White light first for the visible dye tests.
Right. For visible dye, you need bright light. The standard calls for a minimum of 1,000 lux for critical inspections. You need that intensity to really see the contrast of the red indication.
Okay, 1,000 lux minimum. But for fluorescent, it's the total opposite.
Total opposite. You need darkness. A really well-controlled, dark environment.
How dark are we talking?
The standard, ASTM E1417, says maximum 10 lux of ambient white light. 10 lux is very dim, barely enough to see obstacles.
Wow, why so dark?
Because any stray white light washes out the faint fluorescent glow. It kills the contrast between the glowing indication and the dark background. Even a little bit too much light, say 11 or 12 lux, can make you miss critical faint flaws.
So controlling the darkness is paramount. What about the UV light source itself? What's typically used?
The workhorse is usually the mercury vapor arc lamp. It's designed to put out light strongly around 300 to 65 nanometers, which is ideal for exciting most fluorescent penetrants.
But they have quirks.
They do. They need time to warm up, anywhere from 5 to maybe 15 minutes to reach full brightness. And if you shut them off, or the power flickers, they need a long time to cool down before they can restart. Like 10 minutes sometimes?
So not instant on-off.
Definitely not. And their intensity matters too, measured in watts per square meter. Usually around 10 watts per square meter is considered good enough.
Okay, so the lamp needs time, the room needs to be dark. What about the inspector? They need prep time too.
Absolutely. Human physiology. You can't just walk from a bright shop floor into that super dark booth and expect to see faint indications immediately.
Your eyes need to adjust.
Exactly. Dark adaptation. It takes at least a minute. But really, for full sensitivity, it can take up to 20 minutes for your eyes to fully adapt to the darkness.
20 minutes.
For maximum sensitivity, yeah. The rods and cones in your eyes need time. Oh, and a practical tip. Inspectors shouldn't wear those glasses that darken in sunlight, the photosensitive ones.
Ah, because they darken under the UV light.
Right. They darken up in the booth and make it really hard to see.
Good point. Now let's clarify something important the sources highlight. The difference between finding an indication and calling it a defect. Who makes that call?
This is really key for quality control. An inspector finds an indication that's just the penetrant showing a discontinuity, a break in the material.
Okay.
A defect is an indication that's bad enough to reject the part based on the engineering rules or specifications. It exceeds the limits.
And can the inspector make that defect call? Or do they need an engineer?
The sources are very clear. If the technician has the proper certification level, they absolutely can and should interpret the indication and decide if it's a rejectable defect or not.
So they have that authority. They don't need to pass the buck, necessarily.
Correct. Their training and certification empower them to make that critical interpretation.
Good to know. And finally, any safety or maintenance things to keep in mind with UV?
Yeah, safety first. It's like strong sunlight exposure over time. So UV blocking eyewear is recommended to help prevent cataracts. Long sleeves, maybe gloves, a cap can help reduce skin exposure, similar to sun protection.
Makes sense. And maintenance.
Keep those UV lamp filters and the bulbs themselves clean. Dust, oil, grime can build up really fast and cut the UV output drastically,
How much?
easily by 50% or more if they get dirty. And less UV output means lower test sensitivity. You might miss things. So regular cleaning is non-negotiable.
Okay, good advice. Let's shift gears for our last segment. We've talked about automating the process, but what about automating the looking? Mechanized scanning.
Ah, yes, the next frontier. Trying to automate the actual viewing and interpretation of those fluorescent indications. The goal is reliable, repeatable, automated gonna-go decision.
Takes the subjectivity out.
That's the aim. Reduce human fatigue, improve consistency, especially for high-volume inspection.
The sources mention two main ways they try to do this: TV scanners and laser scanners.
Right. The television scanner uses basically a sensitive camera with filters under UV light. But the laser scanner is generally preferred now. It uses a very intense, fine laser beam, often a blue or violet laser, like a helium-cadmium one, at 441.6 nanometers to scan the part, and a photodetector picks up the fluorescence.
Why is the laser better? What's the advantage?
Several things. It usually gives much better detail discrimination. It can see finer things. The contrast between the indication and the background is often much higher.
Easier to see the glow.
Exactly. And a big one is depth of field. The laser spot size determines the resolution, not complex focusing optics, so it's less fussy about the part being perfectly positioned.
Okay, so the laser scans, it sees a bright spot.
Mm.
How does it know if that's a crack or just like a scratch or a tool mark?
Ah, that's the really clever part. Pattern recognition. It uses software, digital processing, to basically mimic how a human inspector thinks.
How so?
It uses algorithms to look at the shape, the size, the intensity of the glowing area. Things like linking adjacent bright spots together to see if they form a line, like a crack would.
And it ignores the random stuff.
It learns to ignore the background noise signals from things like surface roughness, tool marks, minor scratches that aren't relevant flaws based on their shape and characteristics.
So it's trying to tell the difference between a dangerous line and just surface texture.
Precisely. Recognizing the patterns that indicate a real discontinuity versus just background variations.
This tech sounds amazing.
Huh.
Is it replacing human inspectors everywhere now?
Not quite yet, especially not for the really critical stuff like aerospace components where a miss could be catastrophic.
Why not?
Well, while the automated systems are getting incredibly good, the sources suggest that the pattern recognition ability of a well-trained, experienced human inspector, and especially their extremely low rate of false calls, rejecting good parts or accepting bad ones, is still often superior.
So the human brain is still the best pattern recognizer for some jobs.
For now, in many critical applications, yes. Human oversight, interpretation, and final validation are still necessary when the stakes are that high. The automated systems are fantastic tools, increasingly reliable, but maybe not quite ready to take over completely for everything.
That's a fascinating reality check.
Yeah.
So the tech helps us see, but interpreting what we see, that's still key.
It really is.
Well, this has been a great overview. We've gone from, basic spray cans and a field kit,
All the way through stationary systems, big dip tanks.
to fully automated conveyorized lines using electrostatic spray and even laser scanning. It's a huge range of equipment for liquid penetrant testing.
Constantly evolving, too.
Definitely. Before we finish up, just one last reminder about our sponsor. Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training, and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsl3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.
Yeah, definitely check them out. And remember, the goal is always finding those hidden flaws safely and reliably.
Well said. Thanks again for joining us on this deep dive. We'll catch you next time.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support: NDT Level 1, $1 per month; NDT Level 2, $2 per month; and NDT Level 3, $3 per month. Or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, Our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.